unsteady heat conduction equation. I consider the rho T by rho T alpha rho square T by rho x square. Okay, so again I apply the implicit approach to discretize this form. What should I do? Again, consider the same one-dimensional unsteady problem in the explicit approach. So we have a boundary points 1 and 7. In between 2, 3, 4, 5, and 6. Okay. So all the data are now from the initial condition at the nth level. Nth level, all the data or all the temperature now at the each point on a rod. So that's why we are calling another thing. This is n is always be the noun parameter. So how do we calculate the temperature at n plus 1? In the implicit approach. Okay, our objective is again calculate n plus 1 value. Okay, at this location we want to calculate by using implicit approach. So this is the massing direction. This is the temperature along x direction. So here, applying differencing scheme, forward in time, central in space. I can give a abbreviated or a time derivative is a forward and space derivative with respect to a central. So that we have applied in the last class also. Okay, FTCS means the forward in time. And central in space. Applying this scheme here, so what did we get? Di power n plus 1, di power n, del t equal to alpha. For central in space, di n plus 1, sorry, di n 1, di minus 1 at n, 2 di at n, divided by del x. So this is the parameter we have get when apply FTCS scheme. Okay, due to some of the scheme people they calling me FTCS scheme. Okay. So here I am doing one of the interesting concept here. So when give a average values at the noun value. Okay. Average value between the nth level and n plus 1. So what's the time step? Del t, here is the del t. So del t, another name is the time step. I can write to the right hand side of this equation. Alpha del t by del x square. At the I plus 1th location, you can consider you have the I plus 1, I minus 1. You choose that this is I plus 1, this is I minus 1. So you choose any arbitrary points in the field. So I can write that this T I plus 1 at the nth level plus T I plus 1 n plus 1 level divided by. So what I did here, I am averaging the values between n and n plus 1. So that's a new concept I have introduced here. So just introduce averaging between n and n plus 1. That's all. Only right hand side. For I minus 1 location, again, di minus 1, n plus 1 location, nth location. minus 2 again Ti plus Ti. This is for n, this is for n plus 1. Everybody. Okay. So this is the derivative we have taken. Understand? Only right hand side of this equation I have given the average value between n and n plus 1. We will get this. Then if you solve this equation, when you elaborate the right hand side term on the FCC scheme, you will get this value. And the thing is, I want to extract known values are one side, unknown values are another side. Okay. So from the final equation, I want to subtract. Okay, or extract. Known values are one side, unknown values are other. So what are the known value we have now? N are known value. So keep the n value in the right hand side, n plus 1 are in this side. So what are the n plus 1? 1, 2 and 3. Okay. And there is any possibility for saving Ti? Okay, we will arrange next step. Ti plus 1 and minus alpha Lt by 2 del n square and minus alpha Lt by 2 del n square. This is plus this. So you can simulate as the okay. And known values are all the n values are known, as I said. Because of known values always derived from initial condition of our problem. This is a parabolic problem. So in the parabolic approach, I have given what are the condition is must to solve a parabolic problem. We must need initial condition as well as boundary condition. Else otherwise it will be impossible problem. So to solve all the parabola problem, we need to initial condition. So that initial condition gives our initial values. So that initial value I have termed as a nth value. So nth value, that's why we are calling known value. Okay. Now if you look at this final statement of this equation, all the parameters are known. Okay. So all the parameters on the left hand side is unknown. N plus 1 level is unknown. This is our objective from our graph. This is now calculation from initial condition. I want to march along this direction. Now I don't know each point on the line. So, but the boundary point, this one and this one. I mean, this is the 1 and 7. 1, 7 is now 2, 3, 4, 5, 6. Okay. Now can we simplify it? Is it? So Di existing here. Okay. Write Di plus 1. Quotient is 1 plus. Is it? Plus alpha delta by Lect square. And if you look at the another quotient of respective of I plus 1, I minus 1, these both are same. So that's why I introduce a new index for you can consider it as B. Okay. So B represents the quotient of Di plus 1 at N plus 1 level, Di minus 1 N level. Okay, because of both are same quotient. So minus B, Di plus 1 N plus 1. And again minus B, Di minus 1. Is it? This is the left hand side formulation. And when you take the same thing happen in the right hand side also. Di power n quotient is 1 minus alpha Lp by L. Lect square. And this is also the same index of B. What do you want, Ananda? Di plus 1 over n Di minus 1. Is it? Finally, we will get this kind of statement from explicit approach. Now, the same thing also, I can give a quotient value. Here is A. So we already look, so we can consider it as C. Okay. So A of Di N plus 1 minus B of Di plus 1 N plus 1 minus B of Di minus 1. B of C over n. B over So if you look at the right hand side of this equation, final equation, so we can again simplify. Because of all the values are known, I can again give a direct index. Okay, no need to separate index. So I can directly simplify this as can give S plus something. So X. Because of all the values are known. Okay, from the equation del T, del X also known. So del T means the time step. So as a user we need to give a del T value as well as this is the del X. Distance between one node to another node is the del X. So del T and del X we have to fix. Okay, as a CFD engineer we need to fix our del T del X. Okay. Then all the portions Di plus 1 to nth level, all the value are n. So it's again we get from initial depth. So directly I can give H. H I. Okay. H I. This is a implicit form. Okay. Now I want to apply. This is a formation of implicit. This is implicit form. Now question is how to get the value. So when you apply this equation to each given point, again it will form a set of equations. That set of equations you have to transform to matrix. Finally we will solve the matrix. We will get the temperature at each point on the moon. So apply I equal to 2. Okay, when apply I equal to 2, what happens? Equation will be AC2. Is it n plus 1 minus B3 D1 and n plus 1 equal to H1. And if you look at this equation, what I said, so in the left hand side of the equation, D1 is n plus 1. Is this noun? Because of boundary points. Even n plus 1, n plus 2, n plus 3, at the point n, D1 is always noun. Did you understand? So if you even increasing several n plus values, for example n plus 2, n plus 3, keep on going. So at the one node, all the data are down because of boundary points. So our approach is, I need to set the noun value on the other side. Okay. Again, I can reconstruct this equation. And use this such. Okay. J2 plus 1. So the second node produces this equation. Because we are calculating and applying at the node of 2. Okay, this is the equation. You want to calculate the temperature at the second node, you have to use this equation. And when I am applying I equal to 3, cooperate with me. So look, I equal to 3 now.
Yes.
Yes, 3
Minus
3 closer. 3
4
minus
D
2 then I equal to 4. J
D4
Soluda. Okay. Solu. J
N plus 1 N plus
D4
N plus 1 N plus 1
plus 1 B 3. And again 5 A
D5
D5
N plus 1 minus B D4 D6 N plus 1
B
D4
D4.
N plus 1 H5
So when you apply the sixth point, A D6 B 7 B then no need to sound the value, it's a noun from boundary division. D7. That's a boundary point. So we have to set the right hand side up. What index I have used that one? This, that one. Okay. So this is the equation 6. The 5 one. So this is the equation 1, equation 2, 3, and 4, and 5. Okay. So now if you look at our problem, so we have 5 nodes in between 1 and 7. So these are the unknown. Okay, these are the unknown at the n+1 location. So we have a 5 node, 5 equation have been generated. Now how to solve this 5 equation? Again recall your basic mathematics. So how would you write this 5 equation in a matrix form? How do you write this matrix form? Now you have to say all the equations. In form of Ax equal to b. Can you remember? Write all the equation in form of Ax equal to b. So A is again quotient matrix, X is unknown, and B is the boundary points. Okay. So now quotient matrix of the equation 1. So before writing here, you have to write the number of nodes 2, 3, 4, 5, 6. That's also easier to use. So, similar matrix you can directly write. Because of the contribution of 1 and 7 point, you may have a chance to mistake in a write a 1 to 7 node. So that's why I give index again for augmented matrix. So if you look at the equation 1, so what are the parameters available belongs to a D2 available. So what's the quotient of D2? A. D3 quotient?
minus b.
Well, minus b. And fourth quotient?
0.
Fifth quotient?
0.
0 1. Sixth quotient?
0.
0. Is there 3? 3 then. And when you consider second equation, D2 present minus B. D3 A. D4
minus b.
minus B. D5
0.
0. D6
0.
and from third equation D2 D3 minus B. 4
a.
5
minus b.
minus 6
0.
and fourth equation D2 0 1
0.
D3
0.
D4
minus b. minus b.
5
a. minus b.
6 present R
minus b.
and when you consider last equation there is only 6 and 5 is it? So 6 having a quotient and 5 having a minus b. Remaining of 0. This is and this is D2, D3, D4, D5, D6 equal to what are the boundary points? That's 1.
That's 3. That's
3.
That's 4. That's 5.
That's 5.
Is that
That's 2 because of there is a modification I have done here. Okay, that's why I changed the sign. So this is our implicit. When you use the implicit approach in theory, you will get final answer of this matrix formulation. Okay. So now, if you look at this formulation, there is a this diagonal is called main diagonal. This is upper diagonal. This is lower diagonal. So this matrix form contains only 3 diagonals. Okay, that's why we are calling such a tri-diagonal system. So this name is called tri-diagonal system. So still we don't have a get all the temperature at each value. Okay, so each node. So but in a explicit approach, directly we can get all the temperature. Okay, all the temperature directly we can get. But here still we not get. How do we get? Again apply some of the tool to extract all the temperature in the matrix form. Okay, some of the tool is required. So that tool is Thomas algorithm. Thomas algorithm is used to get all the temperature. Okay. So another name is the tri-diagonal algorithm. Both are same. Tri-diagonal algorithm and Thomas algorithm both are same. Right now. Back here. Okay. H2. And time constraint, we would apply implicit or explicit. Okay. So implicit. So if you look at your implicit schemes and equation, first comes from explicit. That's how we derive explicit schemes. So explicit approach and implicit approach. Advantage, disadvantage. So if you look at a explicit method, directly you can get values. So it's a setup a program is easy. Okay, setup a program is easy. If you look at the explicit formula. And disadvantage is, this is the advantage point, and disadvantage point is, so I have said about stability. Stability I will take later on classes. So just to understand the main advantage and disadvantage in explicit. So stability difficult. Stability maintaining is difficult because of there is a constraint in fixing del T and del X. Okay. So there is a constraint between del X and del T. So you should give a low value to maintain the stability of our problem. Yes, otherwise it will not give an exact value. So it will blow up off our computer. It will divergence. So we have to give a minimum value of del T and del X. So these are the main disadvantages in explicit approach. And here is similar. The implicit approach, the setup program is difficult and massive Okay. So why I am saying, just I have fixed 5 nodes in between the boundary points. Okay, at least 5 nodes. So 5 nodes generate a 5 equation. So when you go into a real CAD problem, there is a n number of nodes is required. For example, if you solve even on simple airfoil analysis, it requires 10,000 nodes. So 10,000 nodes, I don't know value. Now imagine 10,000 cross 10,000. So very massive. Okay. And realistic problem, there is a million trillion nodes are available. For example, in this kind of weather prediction. Okay. So weather prediction is very, very massive. Yes, if you look at our map, India map, and above some certain altitude there is a formation of cloudness. So with respect of cloudness area, you have to calculate cloudness, and it's a very large. The cloudness area is always very, very large compared than our bodies, aircraft bodies, airfoils. Such sections compared with this, it's very, very large. So that time you have to put million times of nodes. So it gives a million times of values. So how can we store it? And how can we compose that large number of matrix? So this is a very, very difficult by using implicit. So these are the main disadvantage. So these 2 points are belongs to disadvantage of implicit. Okay. And advantage is, especially it breaks this point. Okay. Advantage of implicit scheme is it can maintain, can stable. Exactly. Can stable large number of del T and del S. Okay. I can give a large number of del T and del S. And it's having another disadvantage is it produces more concussion error. Because of when you have a large number of del T and del X and require more order, and order since gives more concussion error. So if you look at your basic PD equation, what I derived, so right hand side unwanted PD we have to compose with a separate flower bracket. So that terms is the concussion error. So implicit scheme produce a large number of concussion error, large value of concussion error. Okay, this is the disadvantage in implicit. So main advantage of implicit is it has a stable, always stable. So that's why the engineers call it's unconditionally stable. So we don't want to give a condition value. Del T must be less than 0.5, del X must be less than 0.1. Such things never happen in an implicit scheme. So you can give any number of values. Del X not constant, del T is not constant. Okay. So it must give solution. And with respect to our del T, del X, its time consumption also varies. And main advantage is anyhow it's even running up to 2 or 3 days, definitely it will give solution. But explicit it doesn't give a exact solution. Just now when you vary del T, del X, this higher value, definitely divergent solution which takes place in our solution. Okay. So that's why the engineers found out the implicit approach. Scientists are found out the implicit. So implicit approach helps us as well as gives negative rollers. Okay. And what I derived here, that is a crank impulsion. Okay, there is a n number of implicit approaches there. So just I have used crank impulsion approach for your examination point out. As well as explicit approach, also a number of explicit approaches available. Okay. So we have seen the explicit approach last class, that is the FTCS explicit approach. FTCS scheme. So FTCS means forward time, central in space. Okay. So these are the main instruction for our implicit explicit. Important may ask in the 4 months or 2 months. Okay. In your exam. Now, how to solve the tridiagonal class I will tell you how to solve this right angle matrix by using Thomas algorithm. And after solving a Thomas algorithm, we will go to a numerics. So again, numerics is very interesting. Because now when you see a realistic value after getting your problem, the realistic value available, then you have to plot the